Hi everyone, this video is dedicated to very classical results, or I guess pair results, that deal with ring theory, and this is going to be, again, one of a couple of videos that I'm posting as I go off to my first semester of college. So these are going to be shorter in nature and also going to highlight some important results or some theorems in, let's say, analysis and algebra, in this case algebra, that you should probably know. So this one is that ED, which is Euclidean domain, implies PID, principal ideal domain, implies UFD, or unique factorization domain. So before getting into this chain of implications, which is a very well-known result, I'm going to quickly review what it means to be each of these three rings. So a Euclidean domain, or ED, you know what, I'll capitalize, domain, ED. A is a Euclidean domain where A is some commutative ring. If there exists some norm function which behaves the way that the usual norm on the integers works, that is, we have some kind of Euclidean algorithm which works in A. If there exists a function, let's call it delta, from A minus 0 into the non-negative integers, which I'll write as z subscript greater than or equal to 0, such that for any A in A and any B in A minus 0, there exist elements Q and R that are, again, possibly 0, but that are elements of the ring, such that we can express A equals BQ plus R, and we have the following remainder idea with R, this tailing term, such that either R is, well, 0, or delta of R is less than delta of B. So compare this with the usual Euclidean algorithm in the integers, and you'll see that this matches up perfectly. So these just generalize them. Okay, and this is going to be the strongest of the three kinds of rings that we'll consider today, as we'll show by this pair of implications. Now, PID is even simpler. Sorry, let me write down the full name. Principal ideal domain, or PID. A is a PID if for any ideal I, it is principally generated or generated by one element. Any ideal I, there exists some element A such that I is generated only by this element A, that is its principal. Okay, that is, well, A has all of its ideals principal, and so it is a principal ideal domain. So it's also an integral domain. I've swept that under the rug, by the way. All of these are integral domains. So this is necessary in the sense that there's no zero divisors here. This influences factorization, and we have the following definition of unique factorization domain. Or UFD. A is a UFD if for all A in A minus 0, one can uniquely write A is equal to U times, let's say, P1 through P oh my gosh, okay, Pn with U some unit or invertible element and the Pi irreducible. Right? So these Pi in some sense are building blocks in that if you write each, let's say, Pi as the product of two non-units, then it has to equal one of the factors. So this is what we traditionally think of as prime of the integers, although that's kind of a misconception. Prime should really be thought of in its other definition, where an element P is prime if it divides a product AB, then P divides A or P divides B. So these coincide in the integers because the integers are a UFD. And in general, these two notions coincide. Every irreducible is a prime in a UFD. But in more general rings, this need not be true. Every prime element is irreducible, but not vice versa. Okay, so first we want to show that every Euclidean domain is a PID. And you might have seen this proof in the context of the integers, where you're really showing that the integers are a PID by using the Euclidean algorithm to factor. And it's exactly this idea, if you've done this as an exercise or seen it in a course, that generalizes to more general domains, Euclidean domains. So the proof of this fact is reliant on the following fairly clever trick. Let I here be a non-zero ideal. And in the case of 0, obviously that's generated by one element. It's just generated by the 0 element. Take some element B and I of minimal norm delta of B. This exists, although it need not be unique. We don't really need uniqueness here. Then we claim that I is actually generated by B, hence it's a principal ideal. Certainly, we have everything generated by B kept in I to show that the reverse containment holds, that I is in fact contained in B, and hence we have equality of ideals. Take any element A in the ideal, and we can write, because of the generalized Euclidean algorithm, A equals BQ plus R for Q and A. Let me write QR and A, and delta of B, well, actually that's right. Or R equals 0. Well, we must have R equals 0. Since otherwise R, which equals the difference of an element of I, A, and a multiple Q times B in the ideal. So obviously the ideal is a additive subgroup, so it's closed under differences, it's closed under scaling, and so A minus BQ has to lie in the ideal. This is just R. Otherwise R would be of minimal norm. But this contradicts or conflicts with how we have chosen B to be the element of the ideal with the smallest possible norm. This forces R to be equal to 0. Hence, we have that A is equal to BQ, and this is, of course, in B. So because A was in I and it was chosen arbitrarily, we've shown that I is in fact generated by this element of minimal norm. And this shows the proof of the result that every Euclidean domain is a PID just by taking any arbitrary ideal, picking out the element of the smallest possible norm according to which A is a Euclidean domain, and then showing via the generalized Euclidean algorithm that this is in fact what generates that ideal principally. Okay, so this is the first part of what we want to show, and now we want to pass to the second part, which has a slightly more elaborate proof because it's an existence and uniqueness proof that every PID, and hence every Euclidean domain, is a UFD. Okay, so proof. The proof idea is going to be to show that it's impossible to find an infinite sequence of elements of A such that each element of the sequence A sub I is divisible by the next term A sub I plus 1, but they are not associates. So no such sequence can exist. And recall that associate just means that A is associated to B whenever A is a unit times B, or vice versa, because they're invertible. So if they don't differ by a unit, then they're not associates. And let's show that no such sequence exists. So first let me write this claim here. We show no infinite sequence, I should say, of the form A sub n exists where A sub I plus 1 divides AI for all I, and let's say AI comma AI plus 1 are not associates, so they don't differ by a unit. Okay, and what's the idea of showing this, and why can we conclude that the ring is a UFD if no such sequence exists? Well, it shows that if we have an infinite chain of divisibility, then at some point we start having to multiply by units, and so this doesn't really count towards the factorization. If we have this happen, then after finitely many steps, right before we start multiplying by units, then we are guaranteed that a factorization exists. That is, if we start with an arbitrary element A1 and then keep going so that we start dividing by A2, by A3, etc., there's only finitely many elements that can do this, and so as a result, by breaking them down into irreducible components, it is possible to obtain a unique factorization, or at least in this case, a factorization, which in the second part of this proof we will show is unique. Okay, so let's assume such a sequence exists. Okay, and we want to obtain some kind of contradiction. Then the A sub n generates this chain of distinct principal ideals where inclusion does not hold because they don't differ by associates. Remember that associates generate the same ideal. Right? And this goes on indefinitely. So we have a strict chain of inclusion. So now the union of these ideals is principal because A is a PID. Say, let's write this element A to be equal to the union of these constituent A sub i's. Okay? This means that, of course, A is going to lie somewhere on the left-hand side, so it has to lie somewhere on the right-hand side. There's at least one of these ideals that this element A that generates the left lies in. Hence, A is going to be in AN for some n. which implies, right, what does this mean if A is going to be in one of these AN? Well, it implies that everything containing it, of course, must contain A, because these things are obviously increasing strictly. So everything that's contained in, let me put A, M, just to not have too many indices floating around. This contains A for all M greater than or equal to N, i.e. each ideal, if it contains an element, it obviously contains everything that the element generates, but everything the element generates is all of A. So this means that these AI, or AM, are going to equal AN for all M greater than or equal to N, because it contains A, so everything gets generated. So this is a contradiction. Right, it contradicts the fact that these, at a certain point, are not associates, because if they weren't, then they would have strict containment of the ideals they generate. However, if they eventually stabilize, this means that at some point we start getting associates of each other. That is, these ideals are generated by elements that are unique up to multiplication by units. And so these are associates after a certain point, which we've just shown. So this establishes the existence part, which means that we can always find some stabilization of sequences of this form, right? They're always associates. And because of these chains of divisibility that terminate after finitely many steps, we can go back and iteratively factor this element that we started with, this A1. Okay, now we show uniqueness. So each irreducible element P in A generates a maximal ideal. So this is the first part of our hypothesis. That is, in a PID, an irreducible element is going to generate something maximal. Generates a maximal ideal. Why? If P is in something generated, let's say A, that's an intermediate ideal that is in this ring here, recall that an ideal is maximal if in this inclusion, either A is generated by this one element, A, in the middle, right? That is, the whole ring is in this intermediate ideal, or the first two ideals are the same. So there's going to be equality in some step of this chain. Okay, then this means that if we have this inclusion, P is going to equal A times B for some B in A, right? This is because everything generated by P is contained in everything generated by A. So if we have P itself, the element, is going to be something generated by A, which means it's going to be some multiple of A. So P itself equals AB for some element of B. This implies that by definition of irreducible, either A or B is a unit. That is, if A is a unit, then any unit generates the whole ring. So we have equality at this step in the chain. But if B is a unit, then if P is A times a unit, B by hypothesis, then these are associates and they generate the same ideal. This means that P, everything generated by P, is everything generated by A. Okay, so this shows that something generated by an irreducible element in a PID is going to be a maximal ideal. Notice that we wrote this ideal in the middle to be something generated by one element because every element in a PID has this form. So that's where the hypothesis gets used. Okay, thus A mod this ideal, where it's generated by something irreducible, is a field, because every ring modulo a maximal ideal is isomorphic to a field. Okay, so next, suppose an element, let's say, I'll just write A has two factorizations into irreducibles. Let's say P1 through PR equals Q1 through QS. Okay? Then examine the ideals that each of these generate. Let's say the PI and the QJ. Okay, so what about these is important? Let's relabel them. So we're going to relabel this factorization without loss of some generality, without loss of all generality. Without loss of generality, assume that the ideal generated by P1, the first element in the factorization, is minimal among these. Right, and otherwise we can just relabel them, we can switch around the order and say that something else that's minimal is just P1 anyway. So we're going to assume that this first one is it does not strictly contain any of the other ideals, Pi or Qj. We will show that P1 is going to equal Qi for some I. Okay, and this will finish basically everything. So suppose it doesn't. This is yet another contradiction proof. Or suppose it isn't, I guess. Then Pi does not, P1 does not contain any of the ideals Qi. Right? This is because if it's not equal to any of the Qi, and it certainly doesn't strictly contain it because we chose it to be minimal, then it cannot contain any of the Qi at all, actually. Hence, the elements Qi are 0, or sorry, they're non-zero, this is important, modulo the ideal P1 for all I. Right, recall the saying, to contain is to divide. This is a contradiction. This contradicts this factorization here, which I'll call star, whose left-hand side is in fact 0 mod this ideal generated by P1, because of course there's a factor of P1 in this product, which means that everything over here is in the principal ideal generated by P1, hence it is 0 modulo the ideal generated by P1 because it's contained in it, whose LHS is 0 mod P1. Okay, and if the left-hand side is 0 mod P1 and the right-hand side is a bunch of products of things that are non-zero mod P1, then this cannot obviously be an equality that holds in the ring A. So this is a contradiction, and we have shown that P1, this ideal generated by P1, is equal to the ideal generated by Qi for some I. So relabel / assume that P1, we're working at the ideal theoretic level, that the ideal generated by P1 is equal to the ideal generated by Q1. Otherwise, we can relabel so that the ideal that gets generated by some Qi is equal to P1 is in fact Q1, switch around the orders, whatever. So equality of ideals when they're principal just means that the generating elements are associates. So P1 is U times Q1 for some unit U. Cancel. And star, that is P1, let me write P2 PR equals Q1 Q2 all the way to QS. So we have, by this equality here, U times Q1 P2 PR equals Q1 Q2 QS. So obviously these cancel. And so U times P2 through PR is equal to the product of Q2 through QS. Okay? And now we continue inductively. Because a unit times an irreducible element is, of course, itself irreducible, right? This doesn't affect that. You just absorb the unit into whatever factorization needs to happen. So continue inductively. And this shows factorization is unique. Great, and this concludes our proof, having shown existence and uniqueness, both through some kind of clever trick. Okay, so this concludes the results, the pair of results which I wanted to show in this video, which is that every Euclidean domain is a principal ideal domain. That is, as soon as you have a Euclidean norm function, you can say that every ideal in the ring is principally generated. And as soon as you have a PID, that is, every element is principal, then you know that you have unique factorization of elements, which is very useful because not all rings have this. And the ideas in algebraic number theory deal with factorization in rings that are not as nice as UFDs, right? We're very fortunate that the integers are a Euclidean domain, and so hence a PID and then a UFD. And we have unique factorization at the level of elements. But unfortunately, in more general rings, we have to deal with unique factorization at the level of prime ideals. This is the concept in Dedekind domains, and I might make a video on that soon. But for now, we've shown this very important pair of implications, and that concludes the video. Thank you.